This takes a while. I should start earlier next time. So last time we did not have time to finish the things on vector space. I was kind of rushing through the basis things. I think we saw that, like the generating set of vectors is a set of vectors that by linearly combining them, we get all the vectors from the vector space. And a basis is a minimal number of vectors that allow to generate all the vectors by linear combination that are in the vector space. Then we saw the rank of the matrix. So the rank of the matrix, the interesting fact here is that the linear combination, the vectors that you, the dimensionality of the vector space that you get by linearly combining the columns of the matrix is the same as the dimensionality of the vector space that you get by linearly combining the columns and the rows. And that's called the rank of the matrix. So that is basically that the rank of the matrix is equal to the rank of the transpose of the matrix. The vector space that you get by linearly combining the column vectors is called the column space. And the one that you get by linearly combining the rows of the matrix is called the row space of the matrix. So again, the dimensionality of the vector spaces here are the same. Is there a question? No? Okay, I thought you were raising your hand. Okay. Then last week what we talked a lot about was the Gaussian elimination algorithm, and it can be used to compute the rank of a matrix as well. So I think we saw this. So I mean the basic examples usually for the, oh, you don't see anything, sorry. Yeah, sorry. The basic examples that you have usually in vector spaces are Rn, so R3. So here we have the same vector in Rn. We saw this last week as well, I think. And you can express it as a linear combination of elementary vectors or other elementary vectors, and you get the same vector. So that's the basic intuition behind the basis for vector spaces. I think what we talked about also last week is that there's a kind of like fundamental theorem which says that any vector space is isomorphic to a vector space in to some version of Rn, and so that really motivates kind of using examples from Rn. Okay, so one basis is the canonical basis, which is basically you have 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, but you can express Rn with other types of bases, and these are other bases for Rn. I think in the exercise, you already got the exercise sheet. I think there's some exercises on bases, okay. So the set of these three vectors is linearly independent, but not a basis of R4. Because, for instance, this vector here cannot be generated by linear combination of the elements of A. So we can start, so how do we find a basis? We can start by a set of linearly dependent vectors spanning the vectors, and then find a basis for U by by having the set of spanning vectors as columns of a matrix A, solve using Gaussian elimination for a row echelon matrix such that the matrix times lambda is equal to 0. And then we have the linear independent vectors, which are the associated to a pivot, compose the basis of the vector space V in the beginning. So it's just a way to use Gaussian elimination to find a basis for a vector space. So the key thing here is how we compose this, or so we first put all the vectors in a matrix, and then how we specify the problem, which is by saying that the matrix times lambda is equal to 0, which so why do we do this? I ask you guys. Any ideas? What is the definition of linearly independent vectors? When can vectors be linearly independent and not? Yeah?
The only way to get the 0 from the summation is when all the factors are 0. That you can't get one vector of the other vector.
Mm-hmm. So the linear combination of vectors should not be 0.
Except that there's a factor of 0.
Mm-hmm. Except So why do we do this then? Why are we solving? So lambda is our kind of weighing factor, like the balancing factor between the vectors. And why are we transforming this A times lambda equal to 0 in row echelon form, and then reading the pivots there? So this was a way that we set how to find if vectors are linearly independent, and yeah, the pivots in this case are linearly independent vectors of the set. So it means that all the other vectors can be composed out of the vectors there. And so they don't form a basis because they are redundant. Anyways, yeah. Okay, so the dimension of a vector space is the number of vectors in the basis, and it is not the dimensions of it's not the number of coordinates that these vectors have. So if we have a subvector space, remember the definition of a subvector space is that every linear combination of vectors has to be contained inside the set. I'll just remember that, but anyways. So the dimensionality, so the size of the basis that is needed to generate the vector space, if it's a subvector space, it's necessarily smaller than the containing vector space. So that's what I said. It's not necessarily the number of elements in a vector. And I think we took this example, I don't remember. So the vector space V that is spanned by a single vector that has 3 coordinates here, only has dimension 1, and this is actually a line, the vector space that we get by the span of a single vector. Okay, linear mapping, I think we saw this. The important thing to remember, so linear mapping are the same thing that we saw for vector spaces in order to define vectors. So we first define how a vector space is, what are the properties of a vector space, and that allows us to define the properties of what a vector is, but we start by the vector space. This is kind of the same thing, but with matrices. So a linear map in coordinate ends up being a matrix. But we can define what a linear map is independent of its coordinate representation, which again will end up being a matrix. And we do this way. So I think most of you are familiar with linearity. I think I kind of drew it on the board last time when we were looking at the general solution for a set of linear equations, a system of linear equations. So you have, on one side, you have all the vectors that end up kind of canceling the system of equations, so whose solution is 0. And on the other side, you have the particular solutions, so particular vectors that actually are solutions of the equations. And because the system of linear equations is linear, you can decompose it in this way. And that's kind of the definition of what linear is. It's the idea that if you have a function here that takes as input like a weighted sum of vectors, then you can decompose it in this way. Many functions are actually linear. And this comes up over and over again, this definition of a linear map. Anyways, so the important thing here is isomorphism, which is when you have two vector spaces and there exists a linear map that is bijective between the vector spaces, then we say that these vector spaces are isomorphic. So yeah, this is how we define bijective. It's injective and at the same time surjective. So injective means that from the initial set you at least have one solution, or you have a single solution. In the codomain, and then here surjective means that all codomain elements have a preimage in the domain. So anyway, so bijective simply means that every single element on the domain has one element in the codomain, and so you can go back and forth from the domain to the codomain. You can invert the mapping. That's what. So a bijective map is injective and surjective and can always be reversed, and that's the inverse mapping. So of course, if our coordinate version of the linear mapping is going to be a matrix, saying that the linear map is bijective means that the matrix itself can be inverted. I think last week somebody said, well, you can only invert matrices whose determinant is non-zero. So that's what this means here. Yeah, so this was the theorem. So all vector spaces, any n-dimensional vector space is isomorphic to Rn. And yeah, I think we saw this. Okay, so this is on the coordinate representation of a linear map. Yep. These are some graphical representations of linear maps. So today we're going to see this. We're going to see geometry, analytical geometry, and a big part of it is to understand rotation matrices, their properties, and so on. Okay, so I think I didn't show that last week. So the image and kernel of a linear map are subspaces of V, where V is the domain, and W, where W is the vector space codomain. So maybe you guys know what the kernel, what the image and the kernel of a linear map is. What is the kernel of a linear map? No, yeah? Mm-hmm. Yeah. So, and what you're saying, so it's a subvector space of the domain, which, when we apply the transformation to these vectors, the linear map, we get 0 in the codomain. What is the image then? The span of the domain? I mean, span is a particular term. Span means... It has to do with the transformation. Okay, so, I mean, for the kernel, yeah. So one way to write it is by saying it's the inverse of 0, right? So by inverting 0, we get all the vectors. That's just a writing convention here. But the definition is exactly what you said. It's all the vectors in V for which the image is equal to 0. And now, so for the image, we have that it's all the vectors in W such that there exists a vector in the domain that is the result of applying the transformation. So that's why it's called the image. It's whatever vector in W that is the result of the transformation of all the vectors in V. So that's why you meant like the span of V, but it's applied, by applying the transformation. Okay, so graphically this is like this. So you have like a subset of vectors in V and that have image 0. This is called the kernel of the application or the linear map. And then the image is you take all the vectors in V and that ends up being like some kind of subspace in W. Okay, so the null space and column space. So the image of the linear map is also called the column space of the matrix because it's all the vectors that can be composed by linear combination in the codomain of the linear map. So this is what this is saying. So this is the definition of the image in coordinates this time. So that's the difference between coordinates and non-coordinate and coordinate-free thinking. So on one side, we simply define the image like that by saying the result of the linear map are a set of vectors, and in coordinates is simply A times X, right? Where A is the matrix, the coordinate representation of the linear map of V. And yeah, so this is exactly the span of the columns of A. So A is composed of n vectors, n column vectors, and the span of those is the image of the linear map, or it's called actually column space. So as we saw before, the dimensionality of the vector space was of of the column space is actually the rank of the matrix, and the image of V, is called the column space, and the null space is also the general solution to AX is equal to 0. So again, in the coordinate view of the linear map, we can write the kernel like that. Yeah, so it holds, there's a theorem that says that the dimensionality of the kernel plus the dimensionality of the image is equal to the dimensionality of the vector space. Okay, affine spaces. So these are also called linear manifold. Not to be confused with differential manifold, which we'll see later. So in an affine space is simply a vector space that is offset by some constant vector. So here that vector is called x0, the one that offsets all the vectors. And it's also called a linear manifold, or an affine subset of V, and X is called a support point. So these are not vector spaces. They are some kind of offset of a vector space. And the reason why they're not vector spaces is because they don't include 0. No, the neutral element. Okay. So these affine spaces are called also hyperplanes, and this is the parametric equation. Yeah. So when there's only, I said this before, when there's only one vector, the span of that vector is called a line. And this is also true for affine subspaces. So if you have a one-dimensional vector, a one-dimensional vector space that has a support point here called x0, the resulting affine space is also called a line. And if it has two basis vectors, then this would be called a plane. And then in general case, it's called a hyperplane. So yeah, affine spaces are interesting from the system of linear equations point of view, because the solution set of AX is equal to B, so of a general system of linear equations, the solution set is an affine, is a linear manifold, an affine subspace. So all the general solution to, this is called the non-homogeneous system of linear equations. It's called a homogeneous system of linear equations when AX is equal to 0, and I think non-homogeneous when it's equal to B. So this is a linear manifold, or an affine subspace. Okay. Now we have one last slide on affine mappings. So this is just an application, or an affine map is something that takes a linear map plus a support point. And A is called a translation, of course. So every affine mapping is the composition of the linear map and the translation. This is the composition operator here. It's called also a round. And importantly, you can represent it in something called homogeneous coordinates by having the coordinates of the linear map, so the matrix on the top corner here, and then the translation here. So we'll see today, hopefully, if I don't think we're already late, so I don't think we get there, but that this type of coordinate representation, this type of matrices here, define a subspace of the general linear group. So the general linear group is the group of matrices that can be inverted. And I mean, it's a group because they can be inverted. And the operation of that group is the matrix multiplication. And so the matrices that can be written in this way, so where the bottom row is like 0, 0, 0, whatever is the dimension of the matrix, and then you have a little 1 at the bottom corner of the matrix. These define a subset of these, or subvector space actually, of these, of the general group. And it's very important for graphics and robotics and all that stuff, where you have to do rigid body transformations. We'll see that today, hopefully. Okay, so I won't go into the summary because it's already from last week. Let's move on. Unless there are some questions about the lecture from last week. Okay. Okay, so limits of vector spaces. So linear algebra is the study of linear equations. We can model linear equations with vectors. They are very powerful to model geometrical problems. So we saw like systems of linear equations are nice to find solution sets when we have different kind of geometrical shapes, such as lines. When we have generally an intelligent system and we have to model positions in the world, then the positions are going to define a vector space, usually. Velocities also are a vector space. So I use a notation here that comes from differential geometry. So this notation means that we have a manifold here, and we are looking at the tangent space at a particular point of that manifold. So this will become clearer around Christmas, what a manifold is and what the tangent space to the manifold is, and so on. But this is differential geometry, typical notation. Camera images are vector space. The parameters of a neural network model, or like a policy for action or something like that, define a vector space. So these spaces include a notion of similarity distances, which leads to some additional structure on top of the vector space. It leads to the notion of inner product spaces and the notion of metric spaces. So that's what we're going to talk about today. And yeah, so again, I have my example there where I have the orientations of, I have like things that have to do with the self-driving car here, and how these things are all vectors. So you see the kind of Rn type of vector spaces that these things belong to. Again, I think the less intuitive ones is that the camera images also define a vector space, and the vectors are for these images. So these images are represented, or in the most, like in this case, in the most simple case, these are just grayscale images. So it's a matrix where every number in the matrix define the intensity or like the grayscale value. So this thing is also a vector space. But otherwise, more classically, kind of all the quantities that we think in terms of action and perception and state representations, all these things are vector spaces. Okay, so sorry, this is not well compiled. Okay. So first, geometrical spaces. So the first definition that we need to look into is the notion of a norm. So a norm is something that takes in a vector and spits out the kind of length of a vector. So again, if we are thinking outside of the notion of coordinates, this is just taking an abstract vector. It's not. So in this lecture, especially, I don't know if we're gonna then be so picky about the notion of in coordinates or not in coordinates. Maybe when we come back to manifolds, I don't know. But the idea is that if it's just a bold, small letter, lowercase letter, this means that we're not talking about the coordinate version of the vector. It's the coordinate free. And coordinate free means that it's the same. We're talking about a vector independently of the basis in which it is expressed. So, like we saw these 3D representations before. And when we have a coordinate representation, we put a little hat on top of the vector. That means it's a vector in Rn that represents that vector x in a certain basis that is explicit or not, but it's the coordinates of the vector. So a norm is something that is absolutely homogeneous, which means that if we multiply the vector, if we scale the vector, then the norm of the scaled vector is equal to the scaling of the vector times the norm of the vector. And then triangle inequality holds for norms, which means that with the inner operation of the vector space, we have that the x plus y the norm of x plus y is inferior to the norm of x plus the norm of y. That's triangle inequality because it appears. I mean, in Euclidean space in 2D, you have a basic notion of what it means, which means that the straight line between two vectors is going to be smaller than going through an extra point. So then it's positive definite, which means that the norm of a vector is always superior or equal to 0, and that if the norm of the vector is equal to 0, then the vector itself is the neutral element. Okay, so we have two types of norms that I want to take as examples. So the first is the Euclidean norm that you're all familiar with. So if I define the set of vectors such that their norm is equal to 1 in Euclidean space, I get a circle. Then there's the Manhattan norm. So for those of you who are not so familiar with the notion of Manhattan norm, it's called Manhattan norm because if you're in Manhattan and you want to go from point A to point B, you have to walk these streets like these north and then east and then north and then east and so on. And so this is a type of distance between point A and point B. And mathematically, this is expressed like this. And if I draw the set of vectors which norm is equal to 1 in Manhattan norm, then I get this squared here. Yeah. So the Euclidean norm is also called the L2 norm. This is usually how we call it in machine learning. And so what you can see here is that in coordinates, you write, well, so I said I would always have hats or whatever, but here it's implied that the vector x is a vector from n, actually in this case, and it's the square root of the dot product. between the vectors. Today we're going to define what inner and dot products are and how they're different. So general inner products. Again, so we are taking a coordinate-free view. And so we define an inner product space by having a bilinear mapping between two elements of the vector space, which has an image in R. And it is bilinear, so omega is bilinear if it is positive, definite, and symmetric. If omega, on top of being a bilinear mapping, is positive, definite, and symmetric, it is called an inner product and is written this way. So we write inner products like these brackets, using these brackets like that. And the pair of the vector space and the inner product is called an inner product space. So the product space is a vector space and an inner product. So what is bilinearity? So just as we defined linearity, so simple linearity is saying if I have a mapping and I take the kind of weighted sum between two elements, I will get that it's equal to the mapping, the scaled mapping plus the scale mapping of the other element, of the first element plus the scale mapping of the second element. Bilinearity means that if I take in two inputs, my map takes two inputs, then that linearity applies to the first input and to the second input. So that's what's written here. So you have it applied on the first input, and then you have it applied on the second input. Symmetric, we see this all the time. So symmetric simply means that the mapping applied to x and y is equal to the mapping applied to y and x. So there's symmetry in the input. And positive definite, it's a very important concept. It means that if we take any vector that is not the neutral element, the mapping will be greater than 0 or equal to, sorry, what? Is there a typo here? Yeah, I think it should be not equal to 0. Oh, I had some notes about some typos that happened, and I forgot to take them in. Okay, so yeah, so there's a typo, I have to double check here. But positive definite means that it's greater than 0, not equal to 0. It's only equal to 0 if you take in the neutral element. So these coordinate-free definitions will end up, so we will see that the inner product in coordinates ends up involving a matrix representation, and these properties will lead to properties on the matrix that represents that inner product. So we're going to see that. But first, let's see some examples of inner product spaces. So an inner product gives us the general intuitive a notion of an angle between vectors. So, yeah. I mean, what we have here is, yeah, so let's see that. So, an inner product for the real numbers, so one-dimensional vector space, is simply x times y. This is a notion of inner product. So you take two vectors, here vectors are scalars, and you multiply them together, and that's a valid inner product for R. For Rn, what we typically use as inner product is the dot product. And that's the difference between inner product and dot product. It's again something that has to do with coordinate-free and coordinates versions of what we're talking about. So the abstract coordinate-free version is the inner product, which is independent of the basis and blah, blah, blah. And then the dot product is simply that thing here, which is multiplying the coordinates of the vectors together and summing them up. So this is what the definition of an inner product here. There's one view, of course, of matrix multiplications where it's applying, it's kind of applying a bunch of inner products. Yeah. So if we have the vector space of squared matrices, then a valid inner product is to take the trace of A times B transpose, and it's where the trace is actually summing the diagonal terms. And so it's a valid inner product because it is bilinear, symmetric, and positive definite. So in R2, this is something that is not the dot product, an inner product that is not the dot product. So it's another type of inner product. Okay, so I said we'd see like how inner products are represented by matrices. Somebody has an idea of how this is going to work? What is the relationship between, so like some definition of an inner product and then its coordinate representation? What is it gonna be? The result is that basically any inner product is going to be represented by multiplying the first vector and the second vector with a matrix in between. So how would that work? No idea? Yeah, we're going to transpose the vectors, but where would that matrix come from? Like, remember for the linear map, right? We have a linear map that is defined, and then eventually we arrive at a coordinate representation of the linear map that is a matrix. So how did we do that? Okay, well. So the general theorem is that a real valued vector space and a basis, and I think that's the key, is that we are going to reason in some basis. Is an inner product if and only if there exists a symmetric positive definite matrix A, such that the coordinates of A, the coordinates x transpose times this matrix A times the coordinates of y, is equal to the inner product. So first thing, I said that what would end up being the properties of the inner product, which is that it's bilinear, symmetric, and positive definite, would end up constraining the types of matrices that are going to represent our inner product. So this is what it is here. So A is not any matrix. A is symmetric, positive, definite. And we'll define like what that means in terms of what the this constrains the coefficients, the relationship between the coefficients of the matrix. So it cannot be anything. Okay, so the thing is that this is with respect to some basis B. So how do we get A then? So maybe I ask my question again. Like, how do you think we get A? Anybody has an idea? Hmm? So what this theorem is saying is that an inner product is only an inner product if it can be expressed in this way. And A has like some specific structure. But it does involve the basis, right? So the steps to go would be maybe to express the vectors in terms of their basis, and then apply, like the properties that we know that the inner product has. So if you express the two vectors as linear combination of the basis vectors, and then by bilinearity, you get that it's a bunch of inner product between the basis vectors, and this ends up being the coefficients of A. And the coordinates and psi I and lambda j are the coordinates of x and y in the basis. So actually, the matrix A is just a bunch of inner product between the basis vectors. That's what that is. So of course, if you express the same inner product in a different basis, you will get a different matrix A. And that's why it's the coordinate representation of that inner product. And all inner products can be expressed this way. Or consequently, if you have, or like reversely, right? So if you have an expression like this, where A is a symmetric positive definite, what it is, it's defining an inner product on some vector space. And there are many types of A that you can construct that end up being actually just specifying a specific type of inner product on the vectors x and y, on the vector space. Okay. So a symmetric positive definite matrix is a matrix such that if you multiply by x on both sides, it's always positive. Okay, so now we have a better understanding of inner products and their coordinate representations. Then every inner product induces a norm. And so the way it does that is so that's called the induced norm, by just taking the the square root of the inner product of itself, of the vector with itself. And so, but not all norms are induced by an inner product. So in the beginning, we saw the Manhattan norm that is not induced by an inner product. The induced norm satisfies the Cauchy-Schwarz inequality, which is that. And a norm vector space is a tuple of this form, which is a vector space with a norm, which can be an induced norm. So if it's an induced norm, then we kind of get a norm vector space immediately from an inner product vector space, or we call that, inner product space or something in the beginning. Okay, so I'm going to give an example about, I'm going to jump to differential geometry for a quick bit, just to give you an example of what inner products are. So if we have a coordinate map from polar to Cartesian coordinates, what we have, okay. So Cartesian coordinates are defined by, we can use like the canonical basis, remember? So we have 0, 1 if we're in 2D, and then, so 1, 0 if we're in 2D, and then 0, 1. So x and y. The polar coordinates are defined by how far we are from the origin, so a distance to the origin, and then an angle that we are making with respect to that origin. So we can change our coordinate representations. So right now I'm talking about geometrical coordinate systems, not the vector space coordinate systems. So we can change our coordinate representation based on this function here. So this is taking a vector v expressed in polar coordinates, and it's spitting out a vector expressed in Cartesian coordinates. So this is what the value of x is going to be, and this is the value of what y is going to be. Okay, and here we have two vectors. So this one is at approximately 3 meters from the origin and 60 degrees. And then the blue one is 4 meters a bit further from the origin and with a wider angle. Now, we can take the derivative of the coordinate map. That's like really kind of all the key to differential, at least geometrical problems in differential geometry, is that we can take the derivative of the coordinate map, coordinate transform map, right? And that is this thing here. And so we can then express the squared Euclidean line element in this way. So this is saying in Cartesian coordinates, we know that if we are taking a tiny, tiny step in some direction, what we're going to get is dx2 plus dxy. So this is the kind of squared norm. Oh, it should have a 2 here, sorry. Squared norm in some direction. Now, we know that W is equal to phi, and so we can replace W by phi, and then apply the chain rule, here. And okay, so and what we would get here, so we know the coordinate representation, so that matrix here, and the squared norm of that is equal to the square norm of that is equal to that thing times dv times that thing's time dv. So it's just, and so how that ends up, so there's a step missing here, but so by applying the rules of matrix multiplication or matrix multiplication with respect to transpose that we saw last week, you would end up being, maybe I write it on the board. So if you have So we saw that last week. So the thing on the right side, this is saying this matrix, this d phi divided by dv. This is this matrix A. Sorry. This thing is the equivalent of the matrix A here, and X is just this dv. And this thing is just saying we're taking the dot product in R2. And so what we end up having is two metrics which are defined on the what we will call the tangent space. And so in the Cartesian space, the line element here is simply the Cartesian metric, which is the identity. But in polar coordinate, if we want to express the Euclidean line element, so the straight line, in polar coordinates, we're going to have this polar metric here, which is the 1D version of something called the spherical metric. And so it's this idea of kind of computing straight lines on something that is curved. Okay, that's the whole idea of differential geometry. And the way that we get this is by doing A transpose A, so you can check on your own time that if you do that thing transpose times that thing, you get exactly that. And that is the coordinate representation of an inner product on something called the tangent space. And we'll see this later. But this is just an example of using these matrices to represent inner products in coordinates. Okay, so induced distances. So we have, we've talked about how to induce a norm from an inner product. And this is how we induce distances from a norm. So we went from inner product to norm. Norm is just applying the inner product to the vector itself and then taking the square root. And that's the induced norm. And now we are going for the induced distance, which is saying we compute the difference between two vectors and then we apply the norm of that. So that goes with our intuition of what the distance between vectors is going to be. So the norm is induced by the inner product. If the norm is induced by the inner product, we get that the distance between two vectors is equal to that. So just applying the three steps in one go, going from the inner product to the norm to the distance. So in Euclidean space, if the inner product is the dot product, then D is called the Euclidean distance. So that's like the typical distance that you're used to work with in R2, R3. It's just you apply the dot product between the two vectors, and then you take the square root of that. You first you subtract the two vectors, and then you apply the dot product and take the square root. Okay, so the mapping is the induced distance. It's called the map. Yeah. Okay. So it's just what we call metric here is the mapping that takes two vectors and spits out the induced distance. It's called the metric. And the following property hold for that for metrics. It's positive, definite, symmetric, and has triangle inequality. So then again, triangle inequality. I mean, here we are like really reasoning about distances between points or distances between vectors, and so in R2 or Rn, this is we have an intuition of what that means. So yeah, just triangle inequality. Simply that the straight line is shorter than going through a detour point. That's what it's saying. Distances cannot be negative in this context. And if the distance is 0, or the metric between the 2 points is 0, then the points are the same, so the vectors, are the same. I say points because when we start introducing distances, then we are going into this kind of points are the elements of a manifold, and we're going into this direction. But anyways. Okay, so angles. We saw this before, so just using the inner product and the norm of the vectors, we can get a notion of angles between vectors. That equation is actually the definition of angles in R2 and Rn. And so if we have an inner product vector space, meaning the tuple of a vector space and an inner product structure, which again can be only defined in coordinates by a single matrix, then the inner product induces an angle between the vectors, and this corresponds to our intuitive notion of angle in R2 and R3. When using the dot product here, meaning when the matrix associated with the inner product. So what is the matrix associated with the inner product when we're using the dot product? Yeah. So if the coordinate representation of our inner product is simply the dot product, what does it mean in terms of what is the matrix associated with that inner product? And maybe what does it mean with respect to the basis that we are considering? So when using the dot product here for the inner product there, we have our intuitive notion of angles between vectors. What I'm asking is simply, when we do have this assumption here that the inner product is the dot product, what does it mean for the matrix representation of the inner product? And what we consider in terms of basis then? What is the implied basis that we have? Yeah, and then what would be the matrix then? Mm-hmm. So remember, the coefficients of the matrix are the inner product between the basis elements, and in the canonical base is 1, 0, 0, 0, 1, 0, and so on. And if you compute inner products between these basis elements, you can only have 1 or 0. So either the vectors are exactly the same, and the inner product is going to be 1, or the basis element are different and orthogonal. That's what what's the canonical basis is that every basis element is orthogonal to every other basis element. So I just said orthogonal. So what does that even mean? So inner product space is, so this is an inner product space, and we have that two vectors are orthogonal if their inner product is equal to 0. That's actually the definition of being orthogonal. So we write it like this. The two vectors are orthogonal to each other. And if their norm is 1, then the vectors are said to be orthonormal. And the definition of an orthogonal matrix is the following. So remember how we define the inverse of a matrix. We said if we multiply the inverse of a matrix by the matrix itself, then we get the identity. The definition of an orthogonal matrix is just saying A transpose A is equal to identity. So of course this implies that then the inverse of A is equal to the transpose of A. That's like a very fundamental property of orthogonal matrices, is that we can simply invert them by transpose. And the kind of property of the orthogonal matrix is that its columns are orthogonal with respect to the dot product. So if you take two columns of that matrix, their dot product is always going to be 0. Of course, these are only squared matrices. So orthogonal transformations are length preserving. So check out that derivation, also quite important there. So this is exactly what I wrote on the board there. So we are taking, so the length, we measure the length as the dot product of the transformed vector. So we have a vector, we transform it by some linear map. Here our linear map is an orthogonal matrix, in coordinates our orthogonal matrix. We'll see what actually this means without talking about any coordinates. But I think I don't remember. It has a name. But whatever. It's basically rotation matrices. But, okay, so anyways. So we take the image of the vector x through the linear map, and we compute the dot product with itself. And then again, from last week, we know that if we have A times X transpose, this is equal to X transpose times A transpose. This is just matrix algebra. It's one of the most important kind of rules when you're doing matrix algebra. A times B transpose equal to B transpose times A transpose. This allows you to kind of solve things. And this typical derivation here, which is that you want to move A to the left because you know that A is orthogonal and then it cancels out. This is a very kind of typical way of deriving things when you're dealing with matrix equations. Anyways, so that's saying that the length of the image of a vector by an orthogonal matrix multiplied by an orthogonal matrix is still equal to the length of the vector on a squared norm. Second property is that it's angle preserving, and that's the same derivation. We use the same trick. We have our definition of what an angle is. We apply the same trick here, and then what we get is, so that's the angle between the original vectors is the angle between the transformed vectors. Orthonormal basis. So we have the definition of an orthogonal basis. That is that two basis elements are necessary. The inner product between two basis elements is necessarily 0 if they are different. if these two basis elements are different. And if additionally the inner product between the, between the basis and itself, basis vector and itself is equal to 1, then this is called an orthonormal basis. In Rn, the canonical basis is orthonormal, and the inner product is the dot product, which means, this was my question, so then the matrix representation of that inner product is just going to be the identity. So in R2, we have the vectors. We could have like two basis vectors like that. And these guys form an orthonormal basis where their dot product is equal to 0 and their length is equal to 1. Right? I mean, you can check that out. Orthogonal complement. So the idea here is that we have a vector space and the complement is going to be the set of vectors that are orthogonal to that to all the vectors, well, all the orthogonal vectors from the vectors from the original vector space that we are considering. So the orthogonal complement of U is going to be V, and it's all the vectors that have 0 inner product with the vectors U. And actually, so U has to be a subvector space of V, and it's written U. This is for orthogonal. A thing is that the dimensionality of V is equal to the dimensionality of the vectors and the dimensionality of the... yeah, we didn't define V actually. Yeah. So U is a subvector space of V, and it's the complements in V that we are looking for. So the intersection between the vectors in U and the vectors in U, the complement of the orthogonal complement is just the neutral element. And so every vector in the vector space can be decomposed between the vectors in U and then the orthogonal complement. Yeah. So. Mm-hmm. I hope I was recording. Yeah. Okay. Until what time do we have? What is the end of the... So it's still 5 minutes. Okay. Then I think I just finished the section. Okay, yeah. So the end of the section is about function spaces. So, yeah. So functions are also vectors. And I talked about this last week. So functions are defined as being, so you have a range from A to B, and they have an image in the real. And these are vectors. So why are they vectors? Can somebody maybe tell me why? How did we define vector spaces? So what are at least one property of vector space? Yeah? Yeah. Yeah. So how would we apply that to functions? Okay, so we can scale functions by just multiplying so the functions has also a domain and a codomain. So we'd multiply everything in the codomain, and then, so that's one property, and then the other property we have to be able to sum. So how do we, yeah? Yeah. So we can scale the function, which is scaling in the image. And then same thing for adding, we just add, so this is like an example where we have the exponential and the sine function, and then we have the resulting sum, which is another vector from that function space. Okay, so we just add element-wise. That's what it's saying. And we scale, same thing. So the question is now, so in this geometry part of the class, the question is now, how do we define inner products? So the typical inner product on function spaces is by integrating the product element-wise over the entire domain of the function. And like for example, if we have sine times cosine, so if u is sine and v is cosine, the resulting function is odd. Odd means that anything that's on the left of left of zero, basically in terms of image of domain, is going to be the same. No, is going to be the negative of what's on the right side, right? That's what's odd. That's the definition of odd for a function. Even would be the opposite, right? So this implies that the integral, let's say between pi and minus pi, so something you integrate over something symmetric there, is zero. So we would say that sine and cosine are orthogonal to each other because their inner product is zero. So this is graphically what it means. So we have the sine function, and then we have the cosine function, and then we have the inner product between them, or actually the product between them, and the inner product would be the integral. So if we integrate from, minus pi is actually not in the range. So let's say we integrate from whatever point, -2 to +2, because this thing is odd, the integral is going to be 0. So anything that's under the abscissa here, so under here, is the same as what's above, so it's negative. And so these two functions are orthogonal. So that was to give you some idea that vector spaces are not necessarily just Rn. There's function spaces is also a vector space. And so we can define inner product. Okay, so just to conclude on inner product, so let U and V be two functions in the continuous functions, and x and y be vectors in Rn. Then the function space inner product that we just introduced can be approximated by this. So pay attention to the structure of x of this integral when we decompose it as a sum. So it's the sum of individual terms which are xa va plus xa plus dx va x plus d, so that's another term, and so on up to b. So what we're doing is like so if we discretize this thing, discretize the integral, what we're doing is multiplying two elements at a certain point on the image, then go on and adding the multiplication of the image of 2 points and so on. And just to give you some intuition, the finite dimensional vector space inner product, where so we have two vectors and they have coordinates x and y, and we use I should have put hat here, and we use the dot product to compute the inner product between those, will also end up by the sum of little products of their coordinates. So what this means, or the intuition that's behind, is that in function space, what we have is that the image of a certain function defines its coordinates as a vector. So if I have my sine function like that, if I look at the image of the function, right? These are actually somewhat the coordinates of the vector that or it's a way to represent the coordinates. You can have, so that's the most basic way. But if you're then thinking of, for example, Fourier basis, then the coordinates are going to be the Fourier coefficients of the function. But that's just a basic way of thinking about coordinates for functions. So, as the last slide for today, because I'm already running out of time, what we saw today were these, were the inner product space, which is defined by associating a vector space to an inner product. Then we saw we can associate the vector space to a norm, which can be the induced norm, meaning that it stems from the inner product. Then we saw how we can define a metric, which we can then associate a vector space with a metric, which can be the induced metric, meaning that it can also be induced by the inner product, which induces the norm, and then from the norm we induce the metric, and this will lead to the notion of topological spaces. Topological means that there's a notion of neighborhood. So you have not only like vectors defined kind of abstractly, but vectors are defined with respect to how close they are to other vectors. And yeah, so this hierarchy of mathematical spaces, where we have the norm vector spaces are a superset of the inner product spaces and subset of metric spaces, and the inner product spaces are, so these guys, in turn a subset of the topological spaces. So this is what I could do today, and I hope that the recording